different mouth kind of shapes, I guess, as you're singing the vowels, I think we would get a more representative sample overall. So it probably would improve performance on these tests overall.
Thank you.
Yeah, great questions. And then another interesting question was, what would be the main considerations to introduce amplitude-based labels to the database? What type of normalization would or could be used in order to take these into account? So my understanding of that question was, if kind of in addition to these labels that we have just about the technique and the vowel and the key and the speed, like what if we had some sort of label based on the amplitude of the sample? Is that the correct interpretation of that? Like basically saying, tagging this clip with that either a specific like decibel level or just saying, you know, this one's loud, this one's quiet.
Hi, this is my question. Yes, it's the correct interpretation.
Great. Yeah, I think with the task that we were looking to do with the technique classification and the singer identification, we actually ended up normalizing, we normalized the samples so that amplitude wouldn't be taken into account, because we didn't want to kind of bias specific techniques that may be like louder than others. Like if you think about even just for someone kind of belting vibrato or something like that versus like the inhaled technique. So for the task that we were doing, we wanted to kind of remove that factor. But I think I don't know, if you did have a specific task where you really wanted to use that, you could definitely use that as a feature. And I think if I'm understanding correctly, like I feel like if you were to add that as a feature, you probably wouldn't want to normalize anymore like we did. So we normalized to kind of avoid, like remove amplitude from the equation. But if you did want, if you were doing training a model with that as a feature, you probably wouldn't normalize, I would assume. But I don't know, maybe Iran has more ideas on that.
Yeah, all of those are excellent considerations. I mean, when I trained audio models recently, I always normalize the input to the model because I'm not trying to do like a loudness detection algorithm. But if you were to do it, then as Hegel was thinking, Hegel was thinking of this amplitude as a label,
right?
Which could be, yeah, I mean, it would be an interesting regression problem where you regress the loudness or the dB scale of a sound. Something that happens though, which is important to consider when you normalize audio, is that you're not just normalizing the audio, you're also normalizing the noise. Yeah. So if you have a noisy signal to start with, that is very subtle. When you normalize it, you're increasing the loudness of the signal, but you're also increasing the loudness of the noise, which I guess brings to an interesting question. I don't know if you, Julia, did an analysis of like signal to noise ratios in these recordings, or if maybe these recordings were done in a semi-anechoic or /anechoic chamber, and then you didn't have to worry about that. Like, is there anything?
Yeah, we not in like our recording booth wasn't anything fancy, but the noise was very, very low. It was in a booth. But yeah, it would be interesting even to add, like, you could definitely add amplitude just as a label, like as post-processing, like any of you could do that if you wanted to. But I'm sure people are like, it would be an interesting problem to kind of make a regression problem out of predicting it. So yeah, that's a good question. Great. So now to get a little bit into the applications using the data set. So I guess overall, the paper is a data set paper, but typically you'll find in data set papers that they do kind of propose some applications, maybe do some simple baselines, and that's what we did here. So the purpose of the paper wasn't to create kind of the state-of-the-art, most amazing model at these tasks, but more just to show, to illustrate that the data set is useful and kind of we're able to do some interesting tasks using the data set. So we focused on vocal technique classification, so distinguishing between like vibrato, straight, belting, breathy, and so on, and then also singer identification. So we had 20 singers, and can we design this model that can distinguish which singer is singing the input example. So the model input, we basically segmented the audio into 3-second chunks. We normalized the audio, like I was just talking about, kind of to make it amplitude agnostic in a sense. And we fed the raw audio into the model, which itself was a pretty standard 3-layer convolutional network. The output of the model was a softmax. We wanted it to kind of focus and learn to predict the most likely class. And we used the same architecture for both of these tasks, except for the obviously the output layer differed because we had, I think we did on 10 techniques and then 20 a 20 point kind of output layer for that singer identification. So the model did pretty well. It was cool to see a raw audio model being fairly successful in these tasks. The singer identification kind of precision recall scores are a bit lower, which was kind of to be expected because the 20-way classification problem is kind of challenging. On the vocal technique classification problem, we did play around with some data augmentation because we did have definitely a bit of a class imbalance. So you'll see on this confusion matrix with the vocal technique classification that we have very few examples of spoken, things like inhaled, because we just didn't have singers do that for every single example, whereas like vibrato and straight techniques, we did have basically every single kind of like vocalies we proposed, we had singers doing it across those two. So we did have a big class imbalance, and we see that we had kind of more success with vibrato and straight than with our lower cardinality classes here. Any specific questions on this? I got some good questions that I can dig into too, but anyone else have anything else that's coming up right now?
Yeah, in the confusion matrix, the spoken class, it's all zeros on the predictions.
Yeah,
and
so
I was curious about that.
yeah, that's a good observation. So we can see if we look on the y-axis here, we only had maybe 40 total true spoken labeled samples compared to almost 600 from vibrato. So I think that one is kind of an outlier. We only had each singer doing, I think, yeah, two samples as spoken. So I'm not super surprised that we completely failed it at that class in particular, but yeah, I think we could always do kind of some more data augmentation there or something like that to make up for that. But it was good to see success in the kind of more dominant classes, but always something to kind of take into consideration if you're throwing a class in here that has such low cardinality.
I have one question, please.
Yeah.
There must be vocalizations that are harder to do than others.
Mm-hmm.
How do you take that into the account on the model?
In terms of like harder to do for the singer?
Yeah.
Yeah, that's a great question. And this current kind of problem formulation doesn't take that into account. But I think you definitely could play around with something with kind of weighting the different classes in some way if you wanted to address that specifically. Like, you know, I haven't implemented something exactly like that before, but yeah, I don't know, you could kind of bias toward
the question is in the direction of how are you sure that the raw data
mm-hmm.
has a certain level of information that is good for your model?
Yeah, it's a good question. And I think we see here that we didn't give it enough examples of spoken, for example. And I think, you know, we weren't specifically targeting spoken, like that's technically, we wouldn't even say that was a singing technique, I guess. But I don't know, I guess when you really want to kind of focus on those like underrepresented classes, you could do some resampling to kind of oversampling or undersampling down to your minimum class if you did want to kind of account for that class imbalance. Also kind of potentially like weighting things in your loss function, weighting classes that are less represented more, so that the model can learn an even representation from the data set. But it's definitely a challenge that you're kind of always running into in these sorts of larger classification problems. Great. A few more questions I had on some of the pre-processing and the modeling. Let me just refresh on what this question was. Yeah, so we talked a bit about kind of this first one with how we did have kind of vibrato and straight tone really dominating the classes. And then I thought this was a really interesting suggestion. So thank you to whoever kind of wrote this question. But yeah, so the suggestion was, would it be viable to use two models, one that's trained through the raw audio and the other that's trained using spectrograms, and have them supervise each other in a sense. So one model does inference in the time domain and another does inference in the frequency domain. I think that's a super interesting approach. For this project, we were just kind of trying to do the simplest kind of baseline in a sense using the data set. So we weren't trying that hard to get really, really good accuracy. We tweaked the architecture a little bit, but it was more about kind of just showing what we could do with the data set. But I think some kind of paradigm where you're training with spectrograms on one side and potentially the raw audio on the other side could be an interesting way to use kind of both that time and frequency domain. We did try kind of with just spectrograms at the beginning, and we saw actually better results with the raw audio for this experiment, which was kind of interesting. But I think that's a great suggestion. And then why was pitch shifting done in small steps of 0.5 and 0.25? Is it possible to do a key shift augmentation? Yeah, so we did just some in the vocal technique classification, because we do have that big class imbalance. That's why we wanted to do some data augmentation to bring up some of the lower classes. When we did the pitch shifting, we did do it in pretty small steps. In my experience, typically, you'll notice pretty quickly if you really crank up the pitch shifting that your audio can get pretty distorted. And we really wanted to maintain the kind of the timbre of the different techniques and things like that. Like you can imagine if you had one of those lip trill examples or a really kind of high frequency vibrato, that if you, as soon as the audio became a bit distorted, you would kind of lose the kind of sentiment of the technique almost. So I think that's why we just kind of went with two different small steps of pitch shifting. And is it possible to do a key augmentation? You definitely could. So you could do something like, in theory, we're having the singers, telling them this is going to be in C major and giving them a reference tone. We could, in theory, if they sang it perfectly, pitch shift everything a perfect fourth and get our F major. But I think that could lead to some interesting distortions as well with a pretty big jump there. But in theory, it's possible. And then a few more questions on modeling approaches. Why did you decide to train the models and treat them the same way? I thought this was a really great question and showed me that someone was reading the paper very specifically. But yeah, like I said, we didn't spend too much time on the modeling architecture because it was more of an exercise in showing that we could use the data set in this way. So that's basically the simplest answer, is why we just kind of use the same architecture for both. How do we think that the data could be filtered or treated in order to have more precision at the output of the model? I think there's probably more that we could do with the class imbalance. The data augmentation was kind of a first pass at that, but I think we could pull some fancier tricks out of our hat with maybe more, like I said, like weighting the loss in a specific way, upsampling or something like that. I think that would probably be the first next step I would take if I was tweaking the architecture for the specific task, would be kind of taking care of the class imbalance. And then another question, is the only way to be context invariant by limiting the time of the chunk? So I think that's referencing how when we're actually training the model, we took only 3-second chunks where most of the files were a lot longer than 3 seconds. And I did that to kind of try to remove especially in the musical examples. So the ones that I showed samples of were just kind of arpeggios and scales, but there are actual singing excerpts. So I chose to just kind of, use a shorter chunk so that the model wouldn't be picking up on specific kind of trends over a longer span of time. Is there another way of being context invariant or to